magnetism. So today is lecture number 14. Which is the second lecture about magnetism. Is it okay? I mean, no traffic jam, nothing, because I see only 6 persons. Okay. Some spin dynamics. Let us start with the very same Hamiltonian which we dealt last time. Namely, we consider the magnetization, which is a macroscopic quantity, which actually is coupled to external magnetic field. So the Hamiltonian is m dot h. But contrast to previous lecture when we considered thermodynamics of the system and magnetic field was assumed to be uniform and time independent. Now we will be saying that the magnetic field depends on time. So from the very beginning I will start with the quantum problem. So we said that magnetization is connected to the total momentum. Without losing any generality, I will assume that we have just spin, we don't have orbital momentum. Otherwise, everything what I am going to say now should be translated on the language of total momentum. So I will write mu bar S, assuming that G is G factor or lambda factor, which is equal to 2 for the situation when the orbital momentum L is equal to 0. Okay. So just to remind you that G is equal to 2. However, for particular materials, G factor is actually a factor of material. Sometimes it's even can be negative, it's measurable quantity. So this is why I will keep G factor in my calculations. And also Bohr magneton is modulus E H bar over 2 MC. So although I'm going to discuss very simple things today, but what I'm saying is actually very actual now because of quantum computing and quantum information processing. So several equations which I will derive today are directly equation describing behavior qubit, so the two-level system, and you know the spin 1/2 is an example of two-level system. And moreover, in the literature you may see some new words. Namely, I'm going to discuss certain behavior of magnetic field, and in literature it's now called a protocol, because you can manipulate two-level system applying external magnetic field under a certain magnetic field dependence. We will see when I introduce you to the Bloch sphere how the state can be seen on the Bloch sphere, and so on and so forth. But sometimes I will use modern terminology, sometimes I will use old terminology. So the problem is set, and as I said, I will take some magnetic field, actually time-dependent magnetic field, which I'm going to consider, will have large constant component, and I will take a direction of my axis Z, axis quantization for spin, along the constant component. So I'm saying Z would be parallel to some thing H node. So therefore I write it as EZ times H node, plus there will be a small time-dependent component H1 T, which is applied in a direction perpendicular to the direction of the quantization axis. So this is what I'm going to deal with. then we will see conditions when what does physically mean that the time-dependent component is smaller, and we will design certain shape of H1 for solution of problem and solve equation for some particular shape of the time-dependent component. Okay, so spin is a quantum object subject to the algebra, which is SU2 algebra, which says that the commutator of S alpha S beta is equal to I epsilon alpha beta gamma S gamma. This is a spin algebra, right? So let me start with equation of motion for spin. Yeah, if I have bulk system, by the way, just as a side comment, I will write that total spin is the sum over I, all sides, Si. This would be total magnetization, but for the moment, let me assume that we have a just big spin. Okay, so I S alpha dot. Let me write it in a way. I over H bar, commutator of my Hamiltonian, and S alpha. So this is Heisenberg equation of motion for the spin operator. Okay? So let me plug in the algebra and Hamiltonian and derive the equation of motion for the total magnetization. Okay? So this is the logics. I will start with the Heisenberg equation of motion, derive equation of motion for macroscopic parameter magnetization, and then we will construct solution of this equation in some particular situations. Okay, S alpha dot is equal to I over H bar. There is a sign minus. There is G mu Bohr factor here, and then there is a commutator of H beta S beta times S alpha. So this is a scalar product. So therefore it's minus I over H bar G mu Bohr H beta. Again, I remind that I use Einstein notations, which assumes that if I have some repeating indices, I assume summation of all repeating indexes, while I'm not writing it explicitly. This is so-called Einstein notations. So it's commutator over S beta S H. Let me change the order, because you know with the commutator you can change order, and I write alpha beta, and I put sign plus. So this is I over H bar G mu Bohr epsilon epsilon what? S alpha, let me write lambda epsilon alpha beta lambda S lambda times H beta. So times I. This is minus G mu Bohr over H bar. And again, I will interchange indices lambda and beta, put plus epsilon alpha lambda beta S lambda H beta, and this is nothing but vector product. So this is G mu bar over H bar S times H component alpha. Okay? So if I now multiply my equation from the left hand side on the G mu bar and also this on the G mu bar, what I get is M dot. So this is time derivative of the magnetization is equal, I will denote it as some constant gamma times, M dot H. Okay? So this is equation of motion, or dynamical equation which describes time evolution of magnetization. In literature it's called gyroscope equation. There is no dissipation yet, and gamma is equal to G mu bar over H bar. Now I plug in what I have, is equal to modulus E over MC. So for almost 1 hour of this lecture I will be dealing with this equation. So M depends on time, as I said, because the protocol magnetic field depends on time, and we will see what is response. So the goal of this lecture is actually to construct some response functions, dynamical susceptibility, and discuss properties of this dynamical susceptibility. In the last half an hour of this lecture, I will show you what happens with this equation if our magnetization or system of spins is coupled to some bath. So therefore we have dissipation. But for the moment there is no dissipation, and you see that this equation is linear with respect to your magnetization. Therefore, if I assume some summation of a spin on the left and right hand side, nothing changes. I can start with more general moment model, assuming that I have sides, but as long as spin doesn't interact with anything else, in particular spins do not talk to each other, my equation is linear from the point of view of the functions I'm looking for. But you will see that there is hidden nonlinearity in this equation, because vector M, 3 components of vector M are not independent. Any questions so far? Okay, what I suggest for you as a problem is to find dynamics of M square dot. So, which is I over H bar commutator over H and M square. So what you need to do is to compute this commutator, show this is 0, and therefore the M square dot is equal to 0, which means that M square is a constant. I leave it to you as a problem. Okay. They didn't clean this sponge. I'm afraid that the blackboard would be unreadable after few cleaning. Okay, suppose you did exercise. I will assume that M is characterized by components Mx, My, and M naught minus Mz. And M square is equal to M naught square is equal to constant, because M dot is equal to constant. So The logic is I have large time independent component along z direction, which induces large magnetization in this direction, so this is why I put it separately, and all the rest components, namely mx, my, and mz in this parameterization are assumed to be much smaller than m naught. For particular interest, I will now assume that this is h1 t times ex. I can always rotate my axis such a way that I take time-dependent component along x. So what I'm doing, I'm plotting a sphere of a radius m node. So this is x, y, z. So there is a large component h node directed along z. So my point is somewhere here. So this is my magnetization vector, and modulus of magnetization is equal to m naught. And we will see that there is some dynamics of this vector. As I said, since m square is equal to constant, my component mx square plus my square plus mz square is equal to mz m node, which in principle gives me connection between, nonlinear connection between these three components. So I emphasize that although the equation I'm dealing with is linear, it's not really linear because of the fact that these three components are not independent. So there is a hidden nonlinearity. So let's write this equation component by component. So first of all, the vector product m times h is equal to determinant ex, ey, ez. Then I have mx, my, m node minus mz, and I have h1, 0, h node. So h1 depends on time. So this is ex times my h node plus ey times m node minus mz times h1 minus mx times h node plus ez times minus my times h1. So therefore, writing the equation component by component, I have dmx over dt is equal to my times h node times gamma dmy over dt is equal to minus gamma mx h node plus gamma m node minus mz h1 t, and dmz over dt is equal to minus my h1. So these are three linear differential equations.
Yeah. So I was reading about EPR for my like Friday presentation, and there they say about that for a non-anisotropic environment, G is actually a tensor, 3×3 tensor.
Yeah, that's true. But look, I don't want to start with a very general situation and just occupy you with a lot of indices. Let's assume that the situation is isotropic. You are right that in real materials G factor is tensor, which doesn't make any difference. I will just write this equation in a bit more complicated form, which will not, as I said, make any difference. Again, if you like to, we discussed EPR and we discussed neutrons in the last lecture, but this is a lecture. I'm deriving something on the blackboard. Therefore, I would like to start with the most simple example as it is possible. Okay, so this system of equation is still exact. I did not adopt any approximation, but let me do that. So I already said that I parameterize my magnetization in such a way that m small, x, y, and z are much smaller than m naught, and I'm always allowed to do that assuming that h1, so say the h1, if this some function of time and this function is bounded from below and above, so I would assume that maximum of modulus h1 t is smaller than h naught. So if it is so, and I'm going to deal with such problems which satisfy this condition, I should drop all terms which contain the product of two small quantities. For example, here I have mz times h1, therefore I drop this term in linearization, and then since my times h1, I also drop this term and write that this is equal to 0. Again, I'm allowed to do so because this is my condition, and of course I may construct some sort of iteration procedure. We'll solve the equations in lowest order, then plug it in and find the corrections. I'm not going to do that. I assume from the very beginning that these are small quantities and I drop them. So as a result, I got a system of linear differential equations which I'm going to solve. And let me start with solution looking at equation 3. So since dmz over t is equal to 0, therefore mz is a constant. However, using this nonlinear condition, this is some function over mx and my. And actually the condition that this function is function of mx and my will define me some trajectory on a sphere. What kind of trajectory? Let me then look on two remaining equations. So what I want to do, I want to subtract my from this equation by differentiating this equation again with respect to time and plugging in dmy over dt. As a result, I will get a closed equation in terms of mx, and let's see what this equation looks like. Okay, so very easy. D over dt dmx over dt is equal to gamma m d over dt my times h naught. So I wrote that gamma is equal to E over mc. Therefore, gamma times h naught is modulus E h naught over mc. And you recognize that this is so-called Larmor frequency. I will denote it only the note. So I will continue it here. So I plug in So this is then omega naught times minus omega naught mx plus gamma m naught times h1 t, or mx double dot plus omega naught square mx is equal to gamma omega naught m naught h1 t. So what I got is classical equation describing harmonic oscillator, right? Where in the right hand side there is a force which is acting on the harmonic oscillator. So the solution of the linear ordinary differential equation with the right hand side is equal to solution of the homogeneous equation. So homogeneous equation means that this is equal to 0 plus some particular solution of given non-homogeneous equation. So therefore I can write down that mxt is equal to solution of homogeneous equation, general solution, since it's the second order differential equation, is parameterized by two independent constants. Without losing generality, I can write down that this is a cosine omega naught t plus b sine omega naught t plus some solution m tilde xt, which is solution, particular solution of differential equation. One can parameterize with other two constants. For example, one can take amplitude and phase, write a cosine omega naught t plus phi. But whatever you do, you have two linear independent constants. And if you have a problem with initial conditions and certain form of the external force, you need to write down the particular solution and then identify the constant a and b from the initial condition. So let me give you an example. Suppose h1t is equal to h1 cosine omega t. Therefore, external force for harmonic oscillator is equal to gamma omega naught h1 m naught h1 cosine omega t. And you know that one can look for the solution of the differential equation with the right hand side, mx tilde, particular solution, or in literature sometimes it's written particular integral, in the form constant c times cosine omega t, provided that omega is not equal to omega naught. If omega is equal to omega naught, you are in resonance. And then you look for solution with a different form. We will construct some general solution for arbitrary form of h1. Don't worry. So if we do that, we plug it in the linear differential equation, and what we get that omega naught square minus omega square times c is equal to gamma omega naught m naught h1. Now I have cosine on the right hand side and left hand side. I cancel this out. So therefore constant c is equal to gamma omega naught m naught h1 divided by omega naught square minus omega square. So this is the general solution of the non-homogeneous differential equation, and then, as I said, assuming certain initial conditions, you will identify constants a and b, and therefore find the solution of your given problem with initial conditions. Okay? However, let me go further and introduce general susceptibility. Again, what I'm going to write, on the lectures of paramagnetism and diamagnetism, we wrote that magnetization is equal to chi times applied magnetic field. This is what we did, assuming that this is static, uniform problem, namely magnetic field doesn't depend on time and doesn't depend on a coordinate. Moreover, we assumed some isotropy in the problem. If the problem is anisotropic, we will write that alpha component of magnetization is connected with a beta component of a magnetic field through the tensor structure. This would be anisotropic problem when you can start with certain anisotropy of the model. I would assume, and what I'm doing is that the problem is isotropic, therefore I can always diagonalize it, and therefore the tensor of susceptibility, tensor chi is susceptibility, can be brought to diagonal form. This is what one can always do, provided that you have non-zero eigenvalues. And if so, isotropy means that the diagonal form of the tensor is proportional to unit matrix. So all three diagonal components, xx, yy, and zz, are equal. However, in order to write general equation assuming spatial and time dependence, we can write that magnetization computed at a point r and t is connected to the integral dr prime dt prime, some function chi, which is r minus r prime t minus t prime times h at the point r prime and t prime. So then chi, again, being assumed to be isotropic, and therefore instead of writing tensor, I'm writing scalar, all three eigenvalues are the same, is now a function of the coordinate n time. The physical meaning is that you apply magnetic field at some area described by some area coordinates r prime and t prime, and then you look for magnetization induced by this field in some other area of your space characterized by coordinates r and t. In condensed matter, in main body physics, we always need to do some sort of coarse graining. Of course, I can assume that I introduce point like spin in the bulk system, and I'm considering response. But in reality, if I'm applying something, I always assume that this is dealing with certain range of coordinate, and I need to integrate over this range of coordinate, and so on and so forth. Okay, so let's now find the connection between this susceptibility and what is called the green function of the linear differential equation. What I plan to do, I plan to take this linear differential equation and construct a green function for it, and show you that the green function would be proportional to the susceptibility and response function. And of course, I ignore any coordinate dependence because my problem is local in space, but it is non-local in time. So what I will concentrate on is the time dependence. Okay? How to do that? So I'm dealing with a differential equation d2 over dt squared mx plus omega naught square mx is equal some force, external force ft. So I may write down the left hand side as some differential operator which is acting on my mx, and this is ft. when the differential operator LT is equal to d2 over dt squared plus omega naught squared. It's just symbolic way to write down this equation. I didn't write anything new. If I know how to construct the inverse operator, and if this inverse operator does exist, I can write down formally my equation, my solution of this equation, and I'm looking for a particular solution of the linear differential equation in the form that mx is equal to L minus 1t times ft. Or I can write it down as integral from minus infinity to infinity dt prime, delta function t minus t prime, L minus 1 t prime, f t prime. Okay? So this is then, let me denote this. I did a formal trick. I multiplied by delta function, and the integral with delta function gives me the right hand side, right? So let me denote this quantity as g t minus t prime, and what I got is the particular solution of the linear differential equation mx t is equal to integral from minus infinity to infinity dt prime g t minus t prime f t prime. So you see that g and susceptibility are connected. So if I am able to find this function g, then I will immediately find susceptibility. Correct? Good. Let's do that. So if we look then what kind of equation this function g satisfies, we see that I wrote t minus t prime L minus 1 t. You know, I would, without losing generality, I would put delta function here, t minus t prime, in the right hand side. It doesn't matter where I put it when I take integral, but without saying losing generality and defining whether I multiply from the left hand side or from the right hand side, I better write that L minus 1 t times delta function t minus t prime is equal to g t minus t prime. So this is the definition which I adopted. Therefore, if I multiply this formal equation by L, operator L in the left hand side and the right hand side, what I get is L minus 1 delta t minus t prime is equal to LT times g t minus t prime, and since this is 1, I have equation that LT times g t minus t prime is equal to delta function t minus t prime. So this is the equation, differential equation, which my green function satisfies. So this is differential equation for magnetization, and this is differential equation for the green function. Okay, so I'm going to construct the green function taking a Fourier transform. Actually, what I'm saying is part of theory of linear differential equation. Whenever you have a linear problem, you can construct a green function, and green function will give you particular solution of any differential equation as soon as you construct it. I'm constructing this green function based on some particular form of the differential operator which describes harmonic oscillator. Okay, I'm saying that G, I denote T minus T prime is equal to tau. So G tau is equal to integral over d omega over 2 pi G omega e to the power minus I omega tau, and G omega is equal to integral over d tau G tau e to the power plus I omega tau. Okay? Now, let me also recall that delta tau can be Fourier transformed as integral over d omega over 2 pi e to the power minus I omega tau. You remember that Fourier transform of the delta function is equal to 1. This is a white noise. And if I do that and plug in this into my linear differential equation, what I get is d2 over dt square plus omega naught square times integral over d omega over 2 pi minus omega minus infinity to infinity g omega e to the power minus I omega t minus t prime is equal to integral over d omega over 2 pi e to the power minus I omega t minus t prime. So what I see here, that I differentiate with respect to time the exponent, and as a result, comparing right hand side and the left hand side, I get omega naught square minus omega square times g omega is equal to 1. Okay? So therefore, the green function of this differential equation describing oscillator g omega is equal to 1 over omega naught square minus omega square. And what I do now, I will plug in this into this, and so into this, and I find the green function as a function of tau or t minus t prime. Okay, so formally I write that g tau is equal to integral from minus infinity to infinity d omega over 2 pi e to the power minus I omega tau divided by omega naught square minus omega square. However, this is still not fully defined equation. In order to define it completely, I need to take into account very important fact, namely the causality. What it means that if I'm applying something in the time moment t1 and looking for the response at the moment t, I should assume that t is larger than t prime. So, namely, our past defines our future, but not other way around. Therefore, I should say that my green function g at tau positive, which means t minus t prime positive, which means t larger than t prime, or t prime is smaller than t, is something, but g from tau negative, which means t prime is larger than t, and here I have integration over t prime, should be equal to 0. So this is how the response function works. It means causality, and in literature sometimes the function defined like that is called retarded Green function, and even index r is put. R means retarded. So I take integration. So this is my complex plane omega, and I have poles of my expression at minus omega node and plus omega node. So this is the expression which I have here. In order to satisfy this condition, what I need to do is to shift the poles of my Green function a little bit down, assigning some negative imaginary part. A little bit means that I will assign very small imaginary part, and at the end of the calculation I will assume that this imaginary part goes to 0, so I take this limit. Why I'm doing so? Because if now tau is negative, if tau is negative, I have minus I omega tau, which means that this is minus I omega prime plus I omega double prime tau, which is minus I omega prime, this is real part, plus omega double prime tau. So if now tau is negative, I have to take my integration and close the contour in the upper half plane, assuming that omega double prime is positive. And if I shift the poles down, there are no any singularities in the response function. If I take contour like that, the integral will give me 0, because there are no residues, no poles. Therefore, this condition is fulfilled. Now, for positive tau, I need to complete my contour this way. And since there are two poles of the function, I will get some response. So therefore, what I'm saying is that I should replace omega by omega plus I delta, and at the end of the calculations I need to take a limit delta goes to 0. So now this is well-defined quantity, and this is retarded Green function. In principle, you can define complex conjugated function, because now your function is a complex function, which means that it has real part and imaginary part. In principle, you can define a complex conjugated function, which would be called advanced function, has index a, which means that in these integrals, past doesn't matter, and only future defines the present. But these functions R and A are analytic function. They satisfy Cauchy theorem, and they are related to complex conjugation procedure. Good. So now I'm going to compute the integral, which is properly defined. So in your first week, when you got a calculus, I think you discussed properties of complex functions. I don't need to remind you how to take the integral with residues. So this is then, let me split it in two terms. I will write it as 1 over 2 pi. Then I will write it as integral over d omega e to the power minus I omega tau, from minus infinity to infinity. I will write minus, and this is omega minus omega node plus delta, minus 1 over omega plus omega node plus I delta, and I still need to divide by 2 omega node. You see what I did? I have a product omega node minus omega minus I delta, omega node plus omega plus I delta, and since I have product, I can always write as a 2 terms this way. So if I continue, because I want to apply the theorem, the residual theorem, then the integral is given by 2 terms. So in total, this is minus 1 over 2 pi times 1 over omega node, 2 omega node, times minus 2 pi I, minus because I take a direction of my contour clockwise, and the sign plus when you take it counterclockwise, according to the codex. So now residual at this point is equal to 1. So I have e to the power minus I omega tau at the residual omega is equal to omega node plus I delta minus e to the power minus I omega tau at the point omega equal to minus I delta, omega equal to omega node minus I delta, minus omega node minus I delta. So 2 pi and 2 pi cancels out, minus and minus cancels out. What I have is I over 2 omega node. At this residual, I have e to the power minus I omega node tau minus e to the power plus I omega node tau times e minus delta times I minus I gives me minus delta tau. So I will multiply by I and divide by I. I have a minus in the numerator, therefore I flip the sign of the terms in the brackets, so I have sinus, and what I get is that G tau is equal to sinus omega node tau divided by omega node e to the power minus delta tau, and since I said tau should be positive, this is delta function. And now I can take a limit delta goes to 0 from the positive side, so delta is equal, so-called delta plus is equal to 0, and this exponent is gone. I deliberately keep this exponent because we will see in a few minutes that if we have some dissipation in the system, this causality appears automatically. And with the same calculations, we will get the Green function for harmonic oscillator with friction, which describes the magnetic system with dissipation. Okay. So this is the Green function. And therefore, I can write down that this acceptability. Well, first of all, particular solution mx tilde with some external force, arbitrary external force, is equal to integral from minus infinity to infinity dt prime. Then there is the degree function sinus omega node t minus t prime over omega node times theta function t minus t prime. Now I write down the external force, which is gamma omega node m node h1 over t prime. So therefore this is the susceptibility chi xx t minus t prime. So I constructed the susceptibility of the linear problem assuming arbitrary shape of the force. As a homework, just consider previous problem, namely assume that h1 is a cosine omega t, plug it in, compute the integral, and see that we get the same form of particular solution which we got before. Moreover, with the same method, please consider the situation where your drive system, namely your h1t, is proportional to cosine with the same frequency omega naught. What would be the particular solution if we drive system with the same frequency? Okay? Good. Are you with me? So are you still following what I'm doing? You don't hear. So chi xx as a function of t minus t prime is equal to sinus omega naught t minus t prime over omega naught gamma omega naught m naught theta function over t minus t prime. Chi xx omega in the omega frame, it's equal to gamma omega naught m naught divided by omega naught square minus omega plus I delta square. Therefore, it's equal to minus 1 over 2 omega naught gamma omega naught m naught 1 over omega minus omega naught plus I delta minus 1 over omega plus omega naught plus I delta. As I said, this function has both real and imaginary part, and you know that if we have x plus I delta, it's equal to principal value of 1 over x minus I pi delta over x. So this is how we assume and how we define the quantity. So therefore, imaginary part over chi xx omega is equal to gamma m naught over 2 pi. We have a delta function omega minus omega naught minus delta function omega plus omega naught. And the real part is given by principal value. So, as you see, that in the omega space, the imaginary part chi is given by 2 delta functional peaks. This is omega naught and this is minus omega naught. And moreover, you see that imaginary part of chi is odd function of the frequency. You may see that the real part is other way around, is even function of the frequency. You can give this proof by yourself. Yeah. Now, let's assume that we consider the same magnetic system subject to certain dissipation. One can derive the equation which I'm going to show you microscopically, assuming that we have some thermostat or bus we couple our spins to this thermostat, which allows to transfer energy. However, I'm not going to do that. I will just massage my Bloch equation such a way that I have dm over dt.
Excuse me, sir.
Just let me finish. So minus, it's gamma m times h. Yeah?
Yes, I need to understand the essence of bringing in a Green's function, yet we already knew a solution for the differential equation.
And what is unclear?
So what's the essence of bringing in a Green's function, yet we already knew the solution for the differential equation? I just need to understand.
I constructed you the most general way to construct the particular solution of linear differential equation. Since I constructed your green function, suppose you have your differential equation mx double dot plus omega naught square mx, and this is arbitrary function f. I showed you that if this arbitrary function in some particular limit is, say, cosine omega t, I can easily construct particular solution. But let me say that this is not cosine, not sine, but say Bessel function. How are you going to find particular solution of your differential equation? What I presented on the blackboard is a very general way to find this solution, namely your any particular solution mx tilde for arbitrary form of function f is written as integral from minus infinity to infinity dt1 g t minus t1 f t1. And I constructed you the green function explicitly. Therefore, whatever function you have on the right hand side, you can immediately write down the particular solution. You don't need to care about any tricks about guessing what this function could be and so on and so forth. This is the power of green function method. It allows you to construct.
Yes, I understand.
Yeah. So, this was my gyroscope equation without dissipation, which is in component dmx over dt was omega naught and y, dmy over dt equal to minus omega naught mx plus gamma m naught h1 t and dmz over dt was equal to 0. So this was my system of gyroscope equation written down component by component. Just would like to be sure that yes. And what I'm saying now, if I have a dissipation in the system, I should write down something which allows to relax my magnetization. Therefore, I will write down terms minus, and I will write in quote unquote some m alpha over t alpha, and I introduce two relaxation times. You will see how it goes from the bit. Phenomenologically, assuming that there is longitudinal and transverse relaxation. Namely, the relaxation in the direction of magnetic field is called longitudinal. Therefore, I write it as mz over t1. And t1 is a characteristic inverse relaxation time for longitudinal relaxation. And in transverse direction, I assume that there is another characteristic time, t2. So I will write it as mx over t2 minus my over t2. And time in a transverse direction, x and y are equivalent. By the way, what we have seen on the Bloch sphere, let me come back to this sphere interpretation. So we have found that mz component is constant, and what we get is a precession of the magnetization vector on some circle around z axis with a frequency omega naught, which is equal to modulus E h naught divided by mc. So our magnetization precesses with Larmor frequency with respect to z axis and trajectory is so. So if we now allow this dissipation, let's see what happens and what do we get with relaxation. Okay? Again, this is phenomenological way to add dissipation. The equation, the meaning of this equation is different. For example, for mz, this is a sort of kinetic equation which describes the relaxation of magnetization. One needs to deal with microscopic model in order to put some meaning into this T1 and so on and so forth, while for x and y we will see that what was former oscillator will now become oscillator with friction. So far so good. Let's look what happens with this equation. So we have dmz over dt is equal to minus mz over T1. The solution of this differential equation, mz t, is just c times some constant e to the power minus t over T1. So this is why T1 is called the longitudinal relaxation time. Let's suppose that at the moment t naught, your magnetization was on equator. So which means that mz component at t equal to t naught was equal to 0, which means that m naught minus mz t equal to 0 is equal to 0. And mz t is equal to m naught minus mz t. From this initial condition, we will find that c is equal to m naught. And therefore, your mz t is equal to m naught 1 minus e to the power minus t over T1. So therefore, what happens is that your trajectory for mz, it goes to the north pole, and the relaxation describes if you deflect your magnetization vector by putting it on your equator, this relaxation processes describes how fast your system reaches the north pole. Okay? As I said, this is kinetic process. Let's now look at the dynamics of transverse component. And I will do the same. I will exclude my from this equation and obtain the differential equation for m small x. So mx double dot. I differentiate the first equation with respect to time. So this is omega naught my dot minus mx dot over T2. From the second equation, I write that this is omega naught minus omega naught mx plus gamma m naught h1 t minus my over T2. Minus mx dot over T2. So I still have my to be excluded. So therefore I take again this equation and write that my is equal to 1 over omega naught mx dot plus mx over t2. So I need to plug it in here. So what I have is minus omega naught square mx plus gamma omega naught m naught h1 t, omega naught and omega naught, plus and minus mx dot over t2 minus mx over t2 square and minus mx dot over t2. Okay? So this is the left hand side, this is the right hand side. I put everything except external force. This is the external force Ft into the left hand side, and what I get is mx double dot plus 2 times mx dot over t2 plus omega naught square plus 1 over t2 square mx is equal to Ft. What I have is harmonic oscillator with friction. Because in the linear differential equation I have a term which is proportional to mx dot, which is sort of velocity, so to say, and this is a friction. So let me construct the green function using the very same spirit. Okay? This is a still linear differential equation. Nothing happened. The only thing that I have friction here. So now my linear differential operator LT is d2 over dt squared plus 2 over t2 d over dt plus omega naught square plus 1 over t2 square. Right? And the green function satisfies the equation LT g t minus t prime is equal to delta function t minus t prime. And you remember that g tau is equal to integral over d omega over 2 pi minus infinity to infinity e to the power minus I omega tau times g omega. So I'm applying my differential operator and take a Fourier, and what I get is minus omega square minus 2I over t2 omega. Let me write it down, plus 1 over t2 square plus omega naught square times g omega is equal to 1. Okay? You understand what I did? So what is that? This is nothing but minus omega plus I over t2 square. Right? Omega square minus 2I over t2 omega, and then minus I square, and minus give me plus. So therefore g omega is equal to 1 over omega naught square minus omega plus I over t2 square. So you see that in this green function I don't need to do anything and assume retardation, causality, or whatever. The dissipation, so to say, already gives me correct shift of the poles of my green function into the lower half plane of omega, and moreover what I considered as a small, infinitesimally small addition which I needed to do in order to regularize my pole is now related to the dissipation or inverse relaxation time in the xy direction. Okay? And since I computed my integrals keeping delta finite, I can immediately restore what I obtained, namely g tau is equal to sinus omega naught tau divided by omega naught e to the power minus delta tau. This is minus tau divided by t2 and theta function of tau. So this is my green function for the dissipative problem. Okay? So therefore, my susceptibility, by the way, the equations with the dissipations are called Bloch equation. They are used to describe dynamics of microscopic magnetization in the presence of dissipation. When we discuss experiments, you will see that this is indeed the case for EPR experiments and even more sophisticated experiments to identify T1 and T2, in particular spin echo experiments, which actually related to the hidden nonlinearity of equation. But what I will do in the remaining part, I will discuss properties of this susceptibility for the case of dissipation. So, susceptibility chi xx tau is equal to, you remember that tau is t minus t prime, and we assume that tau is positive because of the retardation of causality. This is gamma omega naught m naught times this sinus omega naught tau divided by omega naught e to the power minus tau over t2 theta function over tau. So gxx as a function of omega is equal to gamma omega naught m naught omega naught square minus omega plus I over t2 square. So this is my green function in Fourier transform, or I can write it down as minus gamma omega naught m naught divided by 2 omega naught. And here I have two things, omega minus omega naught plus I over t2 minus omega plus omega naught plus I over t2. So what these two poles mean? Why do I have two poles? Because in my rotation I have a possibility to rotate clockwise and anti-clockwise. So I do have oscillation with which corresponds to rotation with Larmor frequency. These oscillations are now decaying. But two poles with plus and omega naught and minus omega naught are corresponding to clockwise and counterclockwise rotation. So I do see that my dynamic magnetization has poles which describe these two sorts of rotations. On Wednesday we will see that poles of dynamical magnetization are computed approximately for Heisenberg model, namely transverse magnetization below the point of spontaneous symmetry breaking, namely when spontaneous magnetization occurs, you break isotropy because you have some particular direction. So the behavior of transverse and longitudinal magnetization will be different. And the behavior of transverse magnetization describes the poles of transverse magnetization, will describe actually magnons, we will see it. But even now, when we don't have any excitations, we will see that the poles of magnetization describe precession with a frequency plus or minus omega naught and damping related to transverse relaxation time. Let's now write imaginary part chi xx omega. So what I do, I multiply the numerator and denominator by complex conjugated variable. So what I have is minus and minus give me plus, gamma m naught over 2 T2, and I have 1 over omega minus omega naught square plus 1 over T2 square minus omega plus omega naught square plus 1 over T2 square. So instead of delta functional peaks, I have two Lorentzian, and again you see that this property that the imaginary part of this acceptability is odd function of frequency is preserved. So T2 then is associated with Lorentzian broadening of your peaks in imaginary part. Right? So real part of chi xx omega is equal to, I multiplied by complex conjugated, this is gamma m naught over 2. Here it's omega minus omega naught divided by the same denominator, omega minus omega naught square plus 1 over T2 square, minus omega plus omega naught, omega plus omega naught square plus 1 over T2 square. And what I can do, I can change sign here, write it omega naught minus omega. I put plus here and I put plus here. Okay? So what I see, in fact, that real part is indeed even function. I replace omega by minus omega. This term transfers to this one and this transfers to this one. So real part is the even function of the frequency. And the last step which I would like to, last calculation which I would like to make, I would like to study behavior of imaginary part for very small omega. So in the vicinity of origin. So if omega is much smaller than omega naught and 1 over T2. Of course, in order to describe precession, I need to assume that my oscillations are not completely damped, so I have good quality factor, so to say. Otherwise, I will have over-damped oscillations. But if omega is much smaller than omega naught and T2, I can simplify the expression. This is gamma m naught over 2 T2. So this is chi, imaginary part chi xx, at omega goes to 0, times 1 over omega naught square plus 1 over T2 square minus 2 omega naught minus 1 over omega square plus 1 over T2 square plus, omega naught square 2 omega naught. I dropped term omega square, so then I will transfer this expression as gamma m naught over 2 T2. So it would be 4 times omega naught. I just write common denominator, and this is omega naught square plus 1 over T2 square minus 4 omega square omega naught square. Now, since I'm looking for the lowest power in omega, I can disregard this term, and what I obtain is factor of 2, that I have a linear slope. If I will write and this is very important property of bosonic systems, actually, that imaginary part of the response function for small omega is linear. I will come back to this point when we discuss experiment, but this is very important property. Please just keep it and remember it. Whatever bosonic system you have, at low frequencies, the response function should be linear. So summarizing what we discussed today is we started with a very simple gyroscope equation describing dynamics of magnetization. We obtained that under certain approximation, namely that your time-dependent component, the bounds for this time-dependent component are smaller compared to time-independent component, then you can linearize your nonlinear equation and transfer the equation for transverse component to the equation of motion for classical harmonic oscillator, while longitudinal component in this approximation remains constant. We did the same with the friction. We constructed the particular solution for arbitrary shape of the time-dependent component, as long as our approximation is valid, namely our solution is correct when h1 is much smaller than h0. Please, when you solve your homework, please don't forget to add to particular solution the general solution of uniform equation. And if you have a problem with initial condition, when you did that, you apply your initial condition and identify two constants which characterize the general solution of linear differential equation of the second order. Then by knowing it, you know general solution of any problem with initial condition. And by constructing green function explicitly for harmonic oscillator. And I think this is a nice exercise when you're introduced into the field of green functions. Did you use it before for solving linear differential equation, the method of green function? I think you did something with Professor Nersisan, constructing green function for Poisson equation, right?
Yes, for lambda Greenberg. Yes.
Yeah. And we related this green function of linear differential equation with a response function, namely susceptibility. So we computed the susceptibility for linear response problem. In fact, our Hamiltonian assumes that we are dealing with linear response. It's not always the case. The interacting problems are easily becoming a linear problem, and therefore computation of the response becomes much more complicated because you cannot rely on a green function anymore. And then we discussed that the poles of this susceptibility, the response function, characterize the Larmor precession of your magnetization, clockwise or counterclockwise. So this is why we have two poles. If you come back to phonons and remember that we computed electron interaction due to phonons, we did get expression similar like that. So what we got actually is a green function of phonon system, and two poles corresponds to absorption and emission of phonon that case. So the message was that the poles describe the excitations, so to say, in the system. Here in the simple system, excitations means precession, but imaginary part, so real part of the pole, describes the energy of expectation, and the imaginary part describes the inverse lifetime. Here we have Lorentzian shape of the line, and the T2 is just half width. So T2 is nothing but 1 over T2, half width at the half height, while the position of the pole is at frequency of precession. Yeah, that's all for today. Any questions?